So our next one relates volume and temperature. So the volume of a gas and its Kelvin temperature, and I want to make this very, very, very clear, I'm going to underline this a lot, that when we're doing gas law problems, all gas law problems, and let me say that again, all gas law problems, your temperatures need to be in kelvins for these equations to work. So with Charles' law, we have a direct proportionality. Okay, volume and temperature are directly proportional. Okay, that means that if volume goes up, temperature goes up. And if temperature goes up, volume goes up. If temperature goes down, volume goes down. Okay, they move together. Okay, so V1 over T1 equals V2 over T2 is Charles' law. So Charles' law is actually one of the ways that scientists determined the value for absolute zero. So they used Charles' law and they related volume to temperature, and they were able to extrapolate back all the way to if we reached zero volume, what would be the temperature? And that's how they arrived, one of the ways that they arrived at 0 Kelvin is absolute zero. So let's take a look at a problem involving Charles' law. So again, your question is going to be, what is changing? So even if we didn't know that we were going to be doing Charles' law, how would we figure that out? So we have a sample of gas that has a volume of 2.8 liters and an unknown temperature. When the sample is submerged in ice at 0 degrees, so there's another temperature, the volume decreases to 2.5. So I've got 2 volumes and 2 temperatures. Nothing else in this problem is related to any of the other things that you can measure with a gas. So the only things that are changing are volume and temperature. All right, so in this problem, we want to find T1. So we're using Charles' law, and we're going to rearrange to solve for T1. So I'm going to go through those steps because it's a little bit weird if your algebra is not super strong. Okay, so I'm going to multiply T1 to the other side to get it on top. So V1 is equal to V2 T1 over T2. And then I ultimately want to get T1 all by itself. So I'm going to multiply T2 to the other side. So we get V1 T2 equals V2 T1. Okay. And then I'm going to divide V2 to the other side so that I have T1 by itself. So I'm going to do that right down here on the left. So V1 T2 over V2 equals T1. Okay. So this is just showing the steps for the rearrangement of the equation. Okay. So once I've rearranged the equation, remember our temperature needs to be in Kelvin, so I'm going to add 273 to 0 Celsius. So I'm going to have 2.8 liters times 273 K over my V2, which was 2.57 liters. So I end up with 297 Kelvin. Now, here's the question. Does the answer make sense? Your initial volume was 2.8 liters, and it decreased to 2.5 liters when we decreased the temperature. So that means that if our relationship holds, our initial volume should be higher, well, it is higher, and our initial temperature should also be higher. So we started at 270, our initial temperature is 297 at 2.8 liters. And if we cool it to 0, temperature went down, volume went down to 2.57 liters. Okay. And then if we subtract 273, we should end up with 24 degrees Celsius. Okay. So when there are more than two things changing, so with Boyle's law, we have pressure and volume. Charles' law, we have volume, temperature. So two things each. But what if there are more than two things changing in a particular equation? We can actually combine Boyle's and Charles' laws into what we call the combined gas law. So P1V1 equals P2V2, there's Boyle's law, and then V1 over T1 equals V2 over T2, there's Charles' law. So let's take a look at a question involving combined gas law. Boy, I can't speak today. Okay, so we have a sample of gas at an initial volume of 1.5 milliliters, 158 milliliters, and a pressure of 735 millimeters of mercury, and a temperature of 34 degrees C. So I have volume, pressure, and temperature. There's three things there. Then if the gas is compressed to a new volume, so volume is changing, and heated to a temperature of 85 degrees C, temperature is changing, what is its final pressure? So pressure is changing. So that clues us in that we're going to be using the combined gas law. Okay, we have three things changing in this equation. So again, it's useful to make a list. So I have P1 is 735 millimeters of mercury, V1, 158 milliliters, T1 is 34 degrees C, which is 307 Kelvin. Remember, always use Kelvin temperatures. Always, always, always. P2, we don't know. V2 is 108 milliliters. And T2, we're going to put down here in between the copyright. T2 is 85 degrees C plus 273 gives us 358 Kelvin. Okay, so I'm going to take my ideal gas or combined gas law, and I'm going to rearrange it. And I'm not going to belabor the steps, but I hope that you're, after the previous example, your algebra rearranging is on par. So we're going to end up with P1 V1 T2 over T1 V2 equals P2. Okay, so once I have that rearranged correctly, I can just plug in the numbers. 735 millimeters of mercury plus 158 milliliters times 358 Kelvin. And I have that in parentheses so that, just to remind you, that should be a times, to remind you that order of operations here, so just be careful how you're entering things in your calculator. And we have 307 Kelvin times 108 milliliters. So we end up with 1254 millimeters of mercury, and if we are careful with our sig figs, we should be reporting this to 1.25 times 10 to the 3. Now, Avogadro's law, as you might expect, is related to moles. And the deal with that is that if you have more gas, it's going to create more pressure, is going to take up more space, so to speak. So more gas equals more space. So if you imagine a balloon, and if you're blowing up the balloon, you are, putting more moles of gas into that balloon, and the balloon expands to a larger volume. Okay, so Avogadro's law, volume and moles are directly proportional. So as you have more gas, you should end up with more volume. So let's take a look at an example of Avogadro's law. So a 4.8 liter sample, so there's a volume, contains 0.22 moles, right? And N is moles. If I didn't explain that, that's the case. So N is moles. How many additional moles, so there's another N, of helium gas must be added to the sample to obtain a volume of 6.4 liters. So I've got the things that are changing are volume and moles. So Avogadros Law is V1 over N1 equals V2 over N2. Sorry, that's V2. And our task is to find N2, so I'm going to rearrange the equation. N2 equals V2 N1 over V1. So I'm going to plug in, once I've rearranged the equation, all I have to do is plug in the values. So N2, 6.4 liters times 0.22 moles over 4.8 liters gives us 0.29 moles. Okay, thinking about that relationship, that direct relationship. So we started with 4.8 liters and we ended with 6.4 liters. So our volume went up, which means that our moles should go up, and we went from 0.22 to 0.29. So our answer makes sense. Okay, so the ideal gas law, okay, is PV equals nRT. Okay, so the value of R, the ideal gas constant, is 0.08206 liters times atmospheres over moles times Kelvin. Okay, now it's extremely important that you let this guide you for units. Okay, if you have to use R in any equation, the units of R have to match the units of everything else. So since R is a constant, gas constant, everything else has to change to match R. So the units must match R. Okay, so pressure has to be in atmospheres, volume in liters, amount of gas has to be in moles, and the temperature must be in Kelvin. Okay, so some students have referred to the ideal gas law as PIV-NERT, which I found really amusing the first time I heard it because it never occurred to me. But PV equals nRT, ideal gas law. So a thing called STP stands for standard temperature and pressure. Okay, and standard temperature and pressure, the pressure will be 1 atmosphere, and the temperature is 0 degrees Celsius, 273 K. So anytime you see STP in a problem, that immediately gives you 2 pieces of information. Okay, so without explicitly saying 1 atmosphere and 273 K, many problems will say such and such happens at STP. Okay, so that immediately gives you those pieces of information. Now, a convenient thing is that 1 mole of gas at STP, so looking at this first bullet point, 1 mole of gas occupies 22.4 liters. Okay, now this is a useful thing, but I also kind of want you to forget it. Okay, I want you to focus on STP means this. Okay, because it's entirely too easy for students to use that first bullet point in places where it's not appropriate. Okay, so that 22.4 liters only applies when you have 1 mole of gas. That's extremely important to remember. Okay, so let's calculate R at STP and 1 mole of gas. So I'm going to take this out of the way so we can do our work. So PV equals nRT. So if I want to solve for R, I'm going to say R equals PV over NT. Right? So I'm going to plug in the values for STP and the 1 mole of gas. So R equals 1 atmosphere times 22.4 liters, which is the volume at STP of 1 mole of gas, over 1 mole times 273 Kelvin. And when we calculate that, we get a value of 0.08205 and some other digits, And given the limits of these sig figs that we're using, and really we should just be a single sig fig, but we are close enough to the actual value of the ideal gas constant.